Welcome everybody to Season 2, episode I am not sure because my co-moderators think we can't count. All I know that the next one will be Season 3, episode 1. And I'm here with my friends.
Hi everyone, Denise Bruffner, VP of Business Development at INQ. I'm coming to you from sunny Southern California, and happy that we finally have a guest from Southern California. But before we talk to our mystery guest, let's hear from Tommaso.
Hi, good morning everyone. Tommaso De Maria, CEO of Entropic Labs, calling you from sunny Singapore as well. And it's my pleasure to introduce to everyone our mystery guest today, Clarice.
Hello, everybody. My name is Clarice Aiello. I am an early career faculty at UCLA, and my group is the Quantum Biology Tech or Qubit Lab. It's a pleasure to be talking with you. I'm very excited about sharing a little bit of what we do and taking your questions.
We look forward to it. Thank you, Clarice. And I believe you are from Brazil originally. You went to school in my old neighborhood at the L'École Polytechnique in Paris, ended up in the UK, and now, as Denise pointed out, you're in California. So been getting around a lot. Can you kind of summarize that in a minute or two, your little journey across the world and academia?
It's been a long trip, right? As you said, I was born and raised in Brazil. Then I got a scholarship to study in France at the École Polytechnique. If you do not know the École Polytechnique, it's one of the schools that marched down the Champs-Élysées during Bastille Day. And after that, I did my master's at the University of Cambridge, and then I came to America first in the East Coast Shore for my PhD, and then I came to California for my postdocs, and now I'm in Los Angeles, which is a city that I really like, especially without lockdown restrictions. It's a wonderful country. It's a wonderful city. Sorry.
It's a big like a country, but it's a beautiful place. Looking you up, I found myself scrolling through your Twitter a lot, and found a couple interesting tweets there that I'd love to get your reaction on. One of them said, you're about to go on a rant against curiosity-driven research. What is curiosity-driven research, and why do you feel like you have to rant against it?
Cool. So I think that all research is a little bit curiosity-driven, right? But not a lot of people, I think, can impunely say that they do curiosity-driven research. People say that they do curiosity-driven research when they imply that their research is not usually bound by grants or by expectations of grant funding agencies, right?
So the opposite of curiosity-driven research is grant constraint research?
Grant constraint research, or maybe, research that has a very narrow end or something. I think people use curiosity-driven research to mention that, to mean that their research is a little bit more open-ended. And my rant was that I've tried using myself, that I do curiosity-driven research, and academia is full of biases, right? And I think that women and minorities, I don't think it would be well received if they said that they want to do curiosity-driven research. And I think if people can say they do curiosity-driven research, they have a privilege, and that's what the rant was about.
Very interesting. I'm not a scientist, but an entrepreneur, and entrepreneurs have the freedom to be curiosity-driven, or are we bound by investors? Along those lines, right. Another of your tweet says, life is short, time is precious, and there's more exciting science to be done, then there are nice collaborators, and you hereby declare that you're consciously only going to pick people before picking the science. Something that I, as an entrepreneur, try to do, but I only deal with money, which is less important than trying to come up with the revolution in quantum and quantum biology. What are your thoughts around picking collaborators before science?
Well, that's what I'm trying to do. I think that there's more things that can be discovered than there's time for one to do it. And you want to maximize spending your time with people. It's probably very similar in an entrepreneurial setting, I guess, right? When you're doing a startup, you're probably going to cherry pick the right people, the right collaborators. And I think for research, it's very similar in that I'm trying to invest spending my time with people whom I admire, with people with whom I have a good relationship. And I'm sure this will benefit the science itself in the future.
Good. Well, let's learn more about your science, which is at the intersection of quantum and biology. Denise, over to you.
Thanks, André. And I'm a biologist by trade. I'm thrilled to talk biology to someone for once in my life. What is this quantum stuff, right? So Clarice, I love your clever name of the Qubit Biology Tech Lab. That's really cute. Very clever. I'm wondering if you can just tell us a little bit about the biological part of your research for those that haven't heard about it.
Yes, and I'll start with a disclaimer, which is that I am not trained as a biologist, right? So what do I want to do with quantum biology? So I like to call myself a quantum engineer, and I'll get to the biology in a second. There's a whole body of mathematical arguments that say that if you use a quantum object as a sensor, then your measurement is improved. In other words, the sensor quantumness enhances your measurement, improves your measurement. So the field of quantum sensing, of technological quantum sensing, in which I'm trained, relies on using quantum objects to measure very tiny things, from very tiny magnetic fields, electric fields, temperatures, right? And there's evidence, sparse evidence, but enough evidence that we actually want to improve that some living objects, some biological things, they might be using laws that are very similar to the quantum laws the technological quantum sensors use in order to interact with their environment, right? So if that's true, this means that living things might be for a very short time working as a living quantum sensor. So my take is that there's then a lot of potential to start taking techniques that have been developed to study and control technological quantum sensors and start using those techniques onto biological samples, which are then treated as bona fide quantum sensors, right? So my work in particular has to do with studying and trying to control spins in especially proteins. And spins, the quantum property of spin does not have a classical equivalent, and it has to do with how quantum objects interact with magnetic fields. For instance, electrons have spins, atomic nuclei have spins, and it turns out that those spins inside electrons inside proteins might be playing important roles to determine how proteins interact with their environment and how chemical processes are driven within cells and within organisms ultimately. So that's where the biology part kicks in.
Wow, that's fascinating. I'm not sure what else I want to ask. Tomas is laughing at me. I read that you were also looking a little bit at vision. I'm kind of changing the subject. But coming from a neurobiology background, I was interested in what you were looking at in vision, or if you could tell me a little more about that.
Yeah. So there's a lot of very interesting things going on in vision, but one of the things that we research that is vision related is the fact that there's a protein there which acts as a photoreceptor in your eyes, in in the eyes of other organisms, and this protein that is called cryptochrome might be being used by, say, birds to interact with tiny magnetic fields such as the Earth. So it's known that birds and turtles and migrating butterflies, that at least as a partial cue, those organisms, those highly complex organisms, follow the magnetic field of the Earth, which is tinier than the magnetic field that you get from your cell phone if you hold it close to your ear, right? To migrate north-south. And there's some evidence that they do this mediated by a protein in their eyes, or in the antennas of the butterflies, that actually absorb light, and this light is going to give enough energy for some spin-dependent chemical reactions to take place. So that's the extent to which vision is involved in the mechanisms that I study. But this said, the same type of light-driven, spin-dependent chemical reaction that we study, they're also responsible for other things than organismal migration, such as metabolic regulation and other very cool things, and actually also electron transport in say proteins or in other chemical reactions. So yeah, it's all interrelated. It's not only vision, but it's all like, it's crazy if you think how crazy how complex an organism must be to function. And that's something that as a physicist I'm learning to appreciate more and more.
I think there is a tremendous degree of complexity in any organism, even the simple single-celled organism. And so it's always fascinating when you learn more and go deeper. There's so much there that we just don't understand, even though we know a lot. So it's always amazing. And I think that, today, Clarice and I both got a notification that the Los Angeles area is shut down again because of COVID. But when that's over, I think I'm going to start coming to work in your lab one day a week. So
awesome.
I'm warning you. I'm warning
awesome.
you.
Awesome.
I think I love what I'm hearing, and I'm going to hand you off to Tommaso now. Thank you.
Thank you. And just one question. I realize we might be pronouncing your name wrongly. Is that true?
No, that's fine.
No? Is it fine? Okay. Because in Italian, I would say Clarice. And I thought maybe in Brazilian, you would pronounce it that way too.
Oh, interesting. In Brazil, it would be Clarice, but it's close enough to Clarice or Clarice.
In fact, Clarice, you made a comment before we started the recording, and now it makes much more sense, right? Given the introduction that you just shared with us. In fact, I can see how we can, of course, learn a lot about biology thinking from the physics point of view, right? So you're a physicist, you come in and you want to study the complexity of biological systems using the lenses of the physicist, but the vice versa might be true as well. What do you think what is there to learn about physics if you were to look at physical systems through the lenses of the biologist?
Oh, a lot, right? So especially in the quantum sciences, and we're betting on that. We bet that there's this huge phase space that is unexplored, on especially on how much we can learn about quantum strategies, looking at nature, if nature really is harnessing quantum degrees of freedom, for instance. And we know to some extent, at least in pure chemistry, that that's true, right? If nature is using quantum somehow, it's dealing with noise super, super well, because biology happens in a warm, crazily messy environment. So nature must know how to protect coherence and protect quantumness for either long enough, or maybe nature is even optimizing the length that is needed for the time that is needed for a process to be quantum to do something useful. So my question is, when we're developing quantum computers, right, can we learn with nature how to cope with noise, how to manage coherence in some optimal way? That's one thing. The other thing has to do with a spin that I think is actually quite important and not super explored. And that's another thing that we're working in our group now, is that nature is super good at transporting electrons. Okay. And for instance, there is a phenomenon that was first observed in DNA, and only later it started being observed in nanofabricated materials. And this phenomenon is called chiral-induced spin selectivity. And that describes the fact that if you have an electron going through a tiny little structure with mirror symmetry that is called chiral, like hand mirror like symmetry. If the electron has one spin state, it tends to go in one direction, and if the electron has the opposite spin state, it tends to go in the other direction. This means that if you collect, say, the electrons emitted in one end of the molecules thermally, you would expect no spin preference. You would expect to find 50, more or less at room temperature, 50% spins up and 50% spins down, right? And this is not what you find in some chiral molecules like DNA or alpha helices in proteins. You, depending on the material, you find crazy, at room temperature, what's called spin polarizations. Instead of 50-50, you find 60-40, 80-20, 95-5. And for those of you with a quantum background, you might know that one of the important steps of quantum computing is the ability to initialize your qubit states, which could be an electron, right? So this means that, and people who deal with quantum computing, they know that doing initialization of spins is not trivial. It requires a degree of control that is, I mean, it doesn't happen super easily. And given this chiral-induced spin selectivity, what you're effectively doing in the quantum computing language is actually initializing, say, electron spin qubits, right, in a natural way. So how did, and this appears to be true. The experiments are good. We're also doing some experiments on that. So if that's true, nature found its way towards spin, like qubit initialization, right? In a very interesting way that is not control intensive. So how is it doing this? In other words, can we learn with nature, like, some ways of improving the way we do quantum computing, for instance? I'm not saying that one should or would replace Google's beautiful superconducting, right, quantum computer, but can we learn strategies that we can apply onto those super good quantum computing, and those strategies would be inspired by nature. So that's the way that I think nature could help, right? If only we were to pay attention and study it like in a very quantum oriented way.
I love it. It's like quantum control strategies based on biological processes. As a disclaimer to everyone here, we spent a few months ago with Clarice, like for me it was night. So we went well into like Singapore's night talking about these concepts. It was absolutely fantastic. So maybe to wrap up the scientific part, and then you can enjoy Andre's questionnaire. You know, maybe a short answer from you. What is the most exciting project that you're working right now in your lab? What is something that you're really looking forward to, that every day you wake up and you're very excited about?
Yes. So first of all, I need to mention that I'm extraordinarily lucky to be working with a super courageous crowd, right? And I'm so grateful that my lab is in their hands right now. So we have a couple of experiments, and I think that one of the things that we want to learn to do is actually use quantum degrees of freedom to control biology. It's like, even if nature is not using quantum mechanics, can it sustain? Like, can it sustain quantum effects, and can quantum states be controlled at very fast timescales so that there is a physiological effect, right? So we want to learn how to, especially this is what we do is engineer what's called in quantum mechanics light matter interactions. It's interactions between electromagnetic fields and matter and atoms and spins. And we want to use those techniques inspired by quantum mechanics to actually drive physiology. It's a long process. It's like a career goal, but we think that by tuning quantum mechanical things, we can facilitate therapies and the way that chemical processes in the cell evolve, for instance.
It's fantastic. I guess I'm speaking on everyone's behalf. I'm really looking forward to read more and like explore the results that you will be producing. Thank you so much. I loved it. Thanks.
You're also welcome to come spend some time in California in our lab.
If only. Soon enough, hopefully, soon enough.
Yes.
Thank you for the offer. Andre.
I'll take the third day of the week if I get the offer. This sounds like a science fiction movie. Before we get to the questionnaire, I just have to ask, and it's my lack of technical understanding, but you talked about quantum inspired and using that. You also talked about the protein spin, how hypothetically it would be perfectly fault tolerant, naturally initialized. Could you use proteins to build qubits? Is that an ambition?
People, so there's several people thinking about this actually, right? On ways that you can encode qubits in a very, I'm not saying it's absolutely fault tolerant, but in a very good way. So there's a recent paper from the Prescue group on that. There's people in chemistry lab doing exactly this, using molecules as quantum bits in some sense. And if you're curious, there's a recent study from the group of Mike Vasilewski at Northwestern, and they do something like in the title of their paper is like teletransport of information in molecular qubits or something. So there's a lot of people thinking about this, right? Right now, I am not convinced that it would be an improvement on Google's quantum computer, right? but maybe. I mean, we never know what technological advances are, where they're going to take us. So, yeah.
Fascinating. We have the muscle bruised quantum questionnaire, 12 questions, and no right or wrong. We always preface that, trying to get your gut reactions in a sentence or less, hopefully, just to get to know you and your thinking a little bit better. So if you're ready, Clarice,
Yeah.
what would you
Go for it.
consider the principal aspect of your personality?
I am fearless.
What is the quality you desire most in a scientist?
Stop. I love that. You're fearless. That's awesome. All right. Clapping from the crowd. Okay, go on. Sorry.
Fearless Clarice, what is your most desired quality in a scientist?
I think they need to be comfortable with being uncomfortable and be open to talking to people as much as possible.
Do you have thoughts on what your most desired quality in an entrepreneur would be?
I think and I think that a good entrepreneur is an entrepreneur who thinks long term, who could find a way of investing in things with the long term in view. And this means that for things that might make a difference in like 10 to 20 years or something.
Greed is good. I learned that in business school, so it's difficult. Your best virtue?
I strive to be empathetic. I'm not sure. It's my best virtue, but that's what I strive for.
Your principal flaw?
Apart from not being good at math, let me see. I don't have a standard answer for that. Oh my god, let me do some soul searching really quickly here.
I'll take math because I'm horrible at it. So.
Okay, no, but apart from math, I still do not know how to say no, and I should find a way how to say no. Yeah.
What do you appreciate most about working in quantum technologies?
First of all, quantum physics. The quantum laws are a really funky set of laws, and I think it's fun to work with quantum physics, and I think it's mostly uncharted territory where everyone can do whatever they want, and there's still room for a lot of growth.
If not working as a quantum scientist, what would you be most likely doing?
I would most likely be a journalist. Actually, I was admitted to university both at the engineering school and the journalism school, and almost by chance I took the engineering school, but I think my alternative career would be as a journalist.
Your favorite scientist?
That's a hard one. Okay, for full disclosure, a couple of years ago, I would have said Feynman, but that's before I knew of some of the not so square things that Feynman did. So I have some people I would like to be like when I grow up. One of these people is Sarah Keller at the University of Washington. And she's a role model, a mentoring role model. And yeah, I would like to say her name here.
Do you have a favorite quantum computing modality? And we'll include spinning proteins in that, hypothetically.
Well, I really like NV centers for sensing, or color centers in general, and I think that they have a bright future ahead of them. Like color centers in general. That's where, but that's my bias. That's my training bias too.
What is your quantum dream?
My quantum dream is, I think, to really be able to do quantum biology, like to really be able to explore potential quantum processes in biology, that the full toolkit of quantum mechanics can be applied to biological things.
And your quantum nightmare?
I think it's a little bit the hype of quantum in those past years. Maybe it's just it's not too much, but I fear quantum. You know, everything's quantum right now. So someone the other day posted on Twitter like a cereal box that had like a quantum something in a cereal box as a name, you know, and you're like, no, I mean that's so yeah. I think it's my nightmare is like the trivialization of quantum to things that shouldn't be called quantum.
And last question, imagine tomorrow you wake up to a universal quantum computer sitting in your living room. Who would you give it to?
Do I need to give it to anyone? Can I play with it?
You can give it to yourself.
Okay, so I'll probably keep it. Yes.
You'll keep it.
I'll keep it.
All right, you'll keep it. Well, Clarice, it was absolutely fascinating to learn more about your work and get to know you. We need books and movies on what you're doing. This is absolutely fascinating. I'd like to thank my co-moderators, Denise Raffner and our sponsor at IonQ. They make great quantum computers on trapped ions.
Yes.
Our sponsor, Entropica Labs, and Tommaso De Marie.
Thank you.
As well as Cambridge Quantum Computing, who is sponsoring us. And this concludes Season 2 episode. I don't really count very well beyond 10. The next episode will be Season 3, episode 1. We will hope to do a holiday special before the end of the year. And until then, we wish you Merry Christmas, Happy Holidays, be safe. You are now detangled.